All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you're all doing okay today. Today, what I want to spend some time doing is some review. So like I promised yesterday, the goal that I kind of have for today is to get you kind of back into the state of the stuff that you've seen before and doing a little bit of front loading of like, this is the stuff that you've seen before that's pretty directly related to what we're going to be doing in this course. So by the end of today's lecture, in terms of review, what I want you to be able to do is list and describe data structures from previous courses. So this is going all the way back to Comp 1020, mainly in Comp 2140, and then other courses. You're not really taught data structures in those other courses, but you apply or use data structures in those other courses. I want you to be able to apply concepts like design by contract, automated testing, memory management, and debugging. For this one specifically, what we're going to spend time doing today is building a list. We're going to write a list not from scratch, but given some structures like here is the interface, here's the header for this list. I want to apply design by contract. I want to use LLDB to step through the code that we've written. I want to write some small automated tests, and I don't want to dwell too long on it because that's not the purpose of the course. But ultimately, the exercise that we're doing for this, a side goal is dust off C. Dust off a bunch of the C stuff that you might have seen in other courses and kind of remind you of the structure of a C program, how to compile C programs, how to run C programs, that sort of thing. I want you also to be able to describe parts of a computer's architecture. This learning outcome here that we're doing for review is not something that we're going to do really anything with for file systems. This becomes more important when we begin to think about concurrency. So multiple processes, multiple things happening at the same time on a machine, both like no air quotes and then giant air quotes at the same time for realsies and at the same time just giant air quotes for pretends. I'm going to ask you this question anyway, because I think it's important to think about this stuff, to remind ourselves of the stuff that we've seen in other courses. And then the last part, and this is also related to ultimately concurrency as opposed to file system stuff, but just to give us a sense of what this looks like. And this idea here is oh gosh, you're gonna be sick of hearing I++ after a while, but I'm just gonna keep saying it over and over again. We're gonna be thinking about how we take these high-level statements in programming languages and then ultimately how those get compiled down to assembly language instructions. And the idea ultimately that assembly language instructions versus statements in a high-level computer programming language, there's a difference between the two of them in terms of atomicity. I don't know if you've ever heard of this word before, atomicity, or the idea of something being atomic. In computing, the idea of atomic really just means it either fully happens or it does not happen at all. There's no halfway. There's no in between. It's not going to be partially evaluated. It's not going to be partially completed. It will either be fully completed or it will not be completed at all in any way, shape, or form. So we'll talk a little bit about that today. And then the new thing that I want us to do, and this is something that you probably have not seen in any CS course before, is I want you to be able to describe the physical structure of a hard drive. I brought to class a hard drive. I brought a hard drive to class today because I want to show you the physical structure of a hard drive. And a lot of what I want to show you today in terms of the physical structure of a hard drive is related to file systems in the sense that file systems are built on these things. File systems have been designed for spinning disks like this, at the beginning anyway. There are a lot of modern file systems that will take advantage of flash storage. So the kind of storage that you might have in your phone that we pretty typically now have in laptops. But file systems that are typically in use were designed for hard disk drives that are still being used a lot in places like data centers where we have to have lots and lots of disk space. So we'll spend some time taking a look at the physical structure of a hard drive. And my goal for this in terms of describe the physical structure of a hard drive, I'll get to you in just a second, is that I want you to be able to define terms, and like if I were to give you a diagram of a disk, I'd want you to be able to label it. That's what I'm looking for right here. Yeah.
So I own a laptop that has flash storage, but it's not an SSD.
Okay, yeah.
How are those things different? Because I don't understand the difference much, but like, is that part of this like at all, like file system stuff?
So the question is about, I've got a laptop that has flash storage that's not necessarily an SSD, and is that related to file systems? Not really, no. Some file systems can know about things like the type of storage that they're being put onto, but within the scope of this course, that's not something that we're going to be spending a lot of time thinking about. Yeah. Before we do any of this, though, what I did want to share with you is some of the stuff that you wrote to me about what you're expecting to be able to get out of this course. And so I'm going to switch over here. I'm going to go to a full screen projector. And I'm clipping really badly on that, so sorry if you're listening to this later or currently. I'm going to put this down. And what I want to show you is some of the stuff that I saw, and I want to talk about some of the stuff that that you're expecting to get out of this course. So here's one of them. The first thing in this is practical use cases of the course content. How many of you, just by a show of hands, are planning to go out and write an operating system after this course is over? One person wiggled their fingers as if to say maybe. No, nobody. Like very few of you are going to go out and write an operating system. Some of you might go work at Microsoft. Some of you might go work at Google and like work on operating systems, and that would be awesome. Just for the record, I think that would be really cool. But the practical use cases of the course content. So the biggest practical use case of the course content for us, at least from my perspective, in terms of like my experience with doing things like web development, is concurrency. That's going to be the big thing that you're going to get out of this course that has some practical stuff. We're also going to spend a little bit of time talking about design patterns, and that's something that you maybe have seen in Comp 2150, maybe just a tiny little bit. You will definitely see it in Comp 3350 at some point this term if you're taking it or if you have already taken it. But we will spend a little tiny bit of time talking about design patterns as they're applied to systems programming. But the big thing is concurrency, and the big thing about concurrency here in terms of practical application is with web development, you've got lots of web browsers all trying to hit the server at the same time, and they've got this common storage system that's usually a database. And concurrency is all about how do I make sure that these multiple different things that are in that case running literally at the same time, how do I make sure that they don't clobber each other? How do I make sure that they don't mess up each other's data as this stuff is happening? What are the kind of bugs that I can run into when that sort of thing is happening? So that's going to be one of the big things that you'll see with the practical use cases of course content. Lots of people were writing stuff that was a little bit like this. So get closer to the OS for deployment of applications to support high frequency trading, I think. I actually saw high frequency trading a couple times. Catching up on C, I'm delighted that you want to catch up on C with this. And then maybe build a new kind of OS. I'm going to be straight with you. We're not building operating systems in this course. I really want to build an operating system, but that's more of a 4,000 level topic than it is a 3,000 level topic. The stuff that we're doing in this course is going to be like, let's get started with operating systems. Let's figure out how do we use an operating system from some part, and then how do we implement parts of an operating system. Let's see. Here's one that I saw that that was pretty practical. I want to learn more about threading and concurrency. This person also says about asynchronous versus synchronous processes, so about concurrency problems. About concurrency problems here. We will spend a lot of time talking about concurrency problems with this. I really liked this one. be able to explain how operating systems work to a 10-year-old. I really liked that. I really, really like that. I'm not sure that I can explain operating systems to a 10-year-old. My son is not quite 10, but I don't know if I could explain to him what an operating system is yet. I don't know if I can do that. There were a few people that wrote stuff like this, better understanding of operating systems, and to get credits, get an elective checked, pass the course. This one is a little less optimistic. I want to survive and pass. This one is, I think, more optimistic in that they want to pass the course, but there's a giant smiley face there. I liked this one. It says, I want to be able to build a functioning operating system, me, 2025, as if they're going to look back at that and say, like, what a silly person. I also liked this one. I want to become an excellent... I want to become an expert, thank you. Knowledge is power. Currently, I know nothing. This will change. I love that. Yeah, I love that. I was kind of like, pleased is the wrong word, but 2 people wrote separately about their sanity. And then selfishly, these 2, of course, are my favorite. The part here about here's some Dr. Bristow lore. I don't know what kind of lore I have to tell you, but yeah. And then this one, again, selfishly is my favorite. I've been told you're a great instructor. Oh, thank you. Yes. So thank you all for sharing that. I'd love to spend 6 hours and tell you about all the things that I read, but in some of the cases, unfortunately, we can't cover some of this stuff. Like the building an OS stuff, that's going to push up into 4,000 level courses as opposed to 3,000 level courses. If you are still interested in that by the end of this course, come and see me, or I can post on the course webpage some resources that you can use to get started with something like that with the material that we've got. But yeah, so I hope that we are able to get to what you want in general by the end of this course. All right, so let's go back all the way to yesterday. And I want to ask these 2 questions to you again, but I want to ask these 2 questions to you in a little bit more of a structured way than we did yesterday. I'm going to leave this Mentimeter up. So this is a Mentimeter again that is running. And if you are kind of playing along right now, I'm asking the same questions, but I don't want you to answer right away because I'm going to stop at different parts of the code. I want to review the code that we wrote yesterday, and I want to stop at these different parts of the code and pointedly ask these questions about what we're doing. Yeah.
Last time when you talked about like voting other people's things, you didn't turn on voting.
I didn't turn on voting.
Yeah,
Ah.
so that's why there was so many memory stuff.
Okay. I'm sure that voting was on, but
It was.
yeah, it doesn't matter to me. I'm happy to read memory over and over and over again. Yeah. Okay. So I'm going to pop over to my terminal and I'm going to quit this. And the state that I'm in right here in my terminal is that I'm back at where we started last class. I've pushed the changes up to the Git repository, but I want to show you how to get these changes, because every time I do examples in class that are in a Git repository, I'm going to push them to the remote repository. So I want you to minimally see how to get those changes so that you have a copy of the code that we're working with. So once you have previously cloned a repository, you can use the git pull command to get the changes from the remote repository onto your local system. So when I do git pull here, it's going to change what.c. I've also updated the README to describe a little bit more about what.c currently does right now. But generally, I'm going to push these changes that I'm making to the code after class to the remote repository. So if you want to keep a local up-to-date copy, then pull afterwards if you're not playing along with me in class. So I'm going to open up what.c here, and I'm going to push this over to the side. And I'm going to bring up my Mentimeter again, and I'm going to put my terminal over to the side here, and I'm going to pointedly ask these questions. So my first question here is on line 18. What are we asking the OS to do when we call this open function? And what does an OS need to do or keep track of for it to be able to do this for us? So this is my program that's going to be running. I'm asking the OS to do something here with this open function call. What am I asking it to do, and what does the OS need to keep track of to be able to do that? A pointer to the file. Okay, so that's a good point. What I'm doing here, this is a pointer is a good way to think about this, yes. In Comp 2160, just quick thumbs up, very quick thumbs up. If you remember this from Comp 2160, you used functions like fopen, and you used uppercase file asterisk file pointers. Yes, yeah, yes, awesome. Okay, yes. This is new terminology for us right now, this term. This is not a file pointer anymore. This is an integer. It's a plain integer. And the thing that we have here is called a file descriptor. It's functionally the same idea as a file pointer, but it is not the same thing. It's not the same thing. It's not a pointer at all. It's just a number. It's just a plain number. Open the file. We're asking for it to open the file. Yes. Request a file pointer. Keep track of the current location in the file. Yes. Okay, so awesome. That is one thing that it does need to keep track of. Keep track of the current location in the file. When I open this file for reading, and so whether it's readable and writable, when I open this file for reading, the very first time I interact with this file in some way, we're going to be starting at the very beginning of the file. And this takes us all the way back to Comp 1020 now. When we work with files in Java and we start doing like new scanner on that file and we do next line on the scanner, we get the first line in the file the first time we call next line. This is something ultimately that our operating system is keeping track of beneath us. Read the contents of the file. Okay, so that's a fair idea. But at this point, it's not actually reading the file. It's not actually reading the file at all. It does determine whether or not the file exists by name, but it doesn't read the contents of the file yet. It doesn't quite read the contents of the file yet. Open a file with the read-only option. Try its best to translate what.c. So what this is doing is not going to translate anything. It's just going to try to find that file in the file system. That's really all it's going to do here. Keep track of the file at the location, look inside, and keep track of permissions. Yeah, so this file is going to have some permissions. We'll talk a little bit more about permissions a little bit later, but it is going to have to ask the question, can you even open the file that you're asking to open right now? I'm going to move down here, line 24. You should be able to add multiple responses to this. What am I asking the OS to do here? And what does the OS need to keep track of for me to be able to do this? Oh, you know what? I understand better about the voting thing. It says press enter to start voting. Yeah. Yep. But then I don't know if it will stop responses coming in. I don't want responses to stop coming in. Yeah. So I'm just going to leave it the way that it is. Virtual memory of the process and where the memory is allocated. Okay, so yes, both of those things. Virtual memory is like the very last part of our course. So don't worry too much about the idea of virtual memory right now. But yes, the answer is yes. It is definitely keeping track of what memory the process has in terms of its virtual memory allocations. Where the memory is allocated. Okay, so yes, this is an excellent point. It's where the memory is allocated, and also that the memory at that address is allocated, that it has actually been allocated by this program that's running. Allocate memory on the heap with a certain size. Keep track of the available space left in the address space. So yeah, same kind of point here. We're trying to keep track of what has and has not currently been used. Asking for memory, find X number free bytes. So yes, once we're keeping track of both the number of allocated and unallocated bytes, we have to find them here. Keeping track of what memory is allocated, allocate some memory. The size of a char, so this is a good question mark here, but the size of here is an operator that's happening in C. So this is something that would kind of happen when our code is being compiled as opposed to the operating system. Tell the OS to manually allocate the memory on the stack. So this is a good idea. When we're doing malloc, though, this is going in the heap. And again, this is going to be something we'll see later as opposed to what we're thinking about right now with virtual memory, but that's OK. Get a pointer to keep track of that in the heap. Request and memory address, allocated space, specified byte size. Yes. Allocate memory, allocate memory, allocate memory, allocate memory. Awesome. Yes. We all generally have the right idea here. Again, like I said last time, none of this is actually happening in the OS. We'll talk a lot more about this later, but for now, it's enough to just assume that yes, we'll continue along with this happy little lie that yes, the operating system is managing a lot of this stuff for us, but in practice, it's not doing anything with malloc. Here are two more lines. And the ones that I really care about are line 32 and line 34 here. Line 32, if we're thinking back to comp 2160, you would have used functions like fgetS. I want to read a line from a text file. fgetS is pretty high level, and it's a little strange to say that about C, but fgetS is pretty high level because it understands what a line is. It will read a certain number of characters up until the new line character. Read is a system call that just reads bytes. That's all it knows about. And it reads exactly as many bytes as you tell it if there are that many bytes left in the file. lseek is something that you have almost certainly never seen before. But thinking back to where we were talking about open here at the very beginning, where we had to keep track of where we are in the file, lseek is a function or a system call that will allow us to change that location in the file without reading anything. Without reading anything from the file itself, it just lets us say, move to this location right now. And if you can think, does everybody know what a tape is? Do we all know what tapes are? Does anybody not know what a tape is? Okay, thank you. You're making me feel less old. Seeking is like what you think of as a tape fast forwarding or reversing. You're not playing it, you're just moving to some other location arbitrarily without doing anything with the audio or the data that's on that tape. So seeking is like that. So these two lines, what are we asking the OS to do? I've told you a lot about what we're asking the OS to do, but what does it need to keep track of to be able to do that? The bytes to be read, yeah. So the read system call here, we're passing it the file descriptor. And again, functionally, this is the same as a function pointer. This is the unique identifier for this file that we've previously opened. We have to keep track of the bytes to be read so that we can put them into this buffer that we're passing to it. I want to put the data into this location. Just confirming that you are all still connected. Yes? Is it just not showing up? Okay. Forgive me for a moment while I refresh this. There we go. Thank you. The current position of the file, man to read, yeah, okay. The current position of the file gets the first 10 bytes, the current location of the file, the pointer to where we are. So yeah, we have to keep track of where we are. The start and locations of the file. So yeah, absolutely. We have to keep track of where the file actually is on the disk that we're looking at. We're going to know a lot more about that tomorrow, but we have to keep track of where all this stuff is on the disk right now. The current location in memory, so the buffer that we're passing to this, yes. the file itself. The old offset plus 10. So yeah, the offset here, once we do a read, we're pushing this thing that we're going to call the offset into the file. So this is how many bytes we've currently read. And then, excuse me, lseek is also making changes to that. The file encoding, this is a good point to bring up, but at this point, at the level that we're operating at in terms of system calls, our operating system doesn't care about the file encoding. It's literally just bytes. It's just data. It doesn't care if it is a plain text file or an image, or it doesn't care if it's an ISO of the game that you got from wares.com or whatever. It's just data. It's just bytes. And what's in that file doesn't actually matter to the operating system. Is the file actually opened when we read? Is it lazily evaluated? So the file is opened. We get a reference to the file. The file has been found by our operating system when we do the open. And once we have that open, we then know where to find the data on the disk. So it's not actually going to do anything. It's not really, yes, I guess, lazily evaluated. It's not going to read any data from the file until we call read, but it's going to read parts of the file system to get to the file. And again, we'll talk a lot about that tomorrow. Disk seek is different than lseek. I actually don't know what disk seek is, so I don't know if I can answer that question. If the person who answered that, I assume that they're similar. I'm not sure. Sorry, there's a section in the textbook that said talking about disk seek. Well, there's seek time with disks, and that maybe is what you saw. I'm not sure. I will look it up. I will look it up, but not in front of everybody right now.
Not my question.
Okay, okay. All right, okay. The very last thing I want you to answer this question about here is the very last line. When we exit the main function, what is the OS being asked to do, and what does it need to keep track of to be able to do that for us? Free up allocated memory. Yeah, 100%. Oops, I forgot to call free is kind of on purpose here. I mean, I could call free, but then my program ends and the operating system is going to come through and just like clean up everything that my program tried to use in terms of resources that it had. Where to return the value? That's a fair point. We'll spend a little bit more time talking about this when we get to talking about processes in a couple weeks. But processes are able to interact with each other, and process is another way to describe a running program. Processes can have some communication with each other in the form of this return statement here. They can tell another process about how they exited when they were finished. Needs to return control back to whatever process is next in the pipeline. It needs to close all the open files, remove the file from the open file table. So this is related to the free up allocated memory part. Return value and free up memory. Close the main file, stop executing code. The writing output to standard output here, this is a fair point. Standard output is going to be written to as soon as we finish running printf here. Just for the record, printf will cause standard output to have data written to it. Was that the verb that I heard? Clean up assigned memory space for that program, which process and privilege level to return to. So trap and return, if I recall correctly. And that, I think, is coming back to comp 2280. I think you might have seen the word trap there when you're doing that. So yeah, these are all very good points. Our operating system, we're asking it to end, and it's going to have to keep track of pretty much everything that we have been doing up until that point so that it can clean up after us. All right, awesome. The next thing that we're going to be doing is also in this Mentimeter. So if you still have it open, don't close it. but we're going to move on to the next part of our lecture, which is thinking about the data structures and architecture. So operating systems, when we're thinking about operating systems and their implementation, is going to be related to thinking about data structures and architecture, so software design stuff. Operating systems internally use data structures extensively. We're going to see lists, we're going to see queues, we will see trees a tiny bit, we'll see trees a little bit, but we're going to see lots and lots of lists and queues in the stuff that we're working with. Operating systems are designed around computer architectures. So the operating system that we're looking at is generally going to be Linux. Operating systems are designed around the architectures that they run on, and Linux is an operating system that can run on a variety of different architectures. Mac OS, I see a bunch of Macs here. I think probably all of you are Apple Silicon. Does anyone have an Intel Mac still? One person, just you. Okay. Okay, 2 people, 3 people, 3 people. So some people have it. Apple has a nice benefit in that they can design their software and their operating system to be very closely tied to the architectures that it runs on. And so when we heard, this is now getting to be a little older, but when we heard lots of things about how M1 and Apple Silicon are just like magic in terms of battery usage and performance, a lot of that comes down to Apple gets to write their operating system to target specifically the architecture that they're working on. Let's do a quiz about data structures and architecture. Again, this is the same Mentimeter that you were on already if you are still attached to that. So I'll hold this for a second if you want to get joined again, if you lost your connection, and then we'll pop back over to the Mentimeter. All right, I'm going to pop over. I don't want you to vote. No, don't vote. Okay, so data structures and architecture. Here is our very first question. The first couple questions are about data structures. Good, yeah, excellent. Yes, I'm delighted that we're all on the same page about the difference between stacks and queues. Okay. All right, okay. This is now me being a little bit pedantic about the difference between an abstract data type and a data structure. This is me being a little bit pedantic about that. A data structure is like the actual material thing that you'd use to implement this. So an array is definitely a data structure that you could use to implement this abstract data type. Stack being we're steps, like the stack of macarons that we have here, we're stacking things on top. We could use an array to do this. An array is maybe not the best choice in terms of I want to have an infinite number of nodes in my stack, but I could use an array to implement this stack data type. Linked list and list here, this is me being pedantic about the differences between an abstract data type and a data structure. A list is an abstract data type upon which we can apply operations. We can insert into a list. We can count how many things are in a list. We can traverse a list. We can iterate over a list. A linked list is the way that we actually implement a list structure. A linked list is one where we're using nodes. A linked list is one where we have pointers from one node to the next. A list is an abstract data type that I could implement with an array. It would not be a very good list, but I could do it. I could definitely do it. Hash table, I guess technically you could implement a stack with a hash table. I guess. I don't know why you would though. That's like question mark in my head. I'm not really sure why you'd choose that. And nobody picked binary search tree, so I'm happy to leave that there. This is 100% me being pedantic about the differences between data structures and abstract data types here. Here's our next question. Good, yes, yeah, excellent. A tree is really the best way to represent these abstractly as this abstract idea. We have files that are within folders. We have folders that are within folders. We've got a tree structure that starts at the root at the very top of the thing that we've got here. This is pretty tight. I don't know. I can't tell the difference between people picking their names and just choosing them randomly. But I'm delighted by magical rhino being attached to a unicorn here. Yes.
Like you can't actually choose it if you like. I was trying to type
Yeah.
it in, but like you move forward, so I can't
Okay.
type my name.
I know that you can make the choice.
Yeah.
So our next two questions here are about computer architecture. So this is going back to Comp 2280, if you're keeping track. This is me being pedantic again. This is me being ultra pedantic. And to be clear, I would never ask you a question like this on a test. I don't actually care about the differences between these things. It's really the idea that I care about what the program counter is. But the program counter is keeping track of the next instruction to be executed. I'm really happy that we all picked these two center options, but really pedantically and really like picky here, the program counter is the next instruction to be executed, not the one that we are currently executing right now. But again, I'm never going to ask you a question like this on a test. Like, I don't care about this stuff. Yeah. Okay. As the note says here, you can assume we're using LC3 for this. All right, okay, so yes, 3 is the correct answer here. 3 100% is the correct answer. And that leads us to our next question. Please forgive the formatting of my assembly language here. It's a limitation of Mentimeter. They don't really care much about people using assembly language instructions as options for answers. So yes, I++ is 3 instructions, and I++ translates to load. Take a value from memory and put it into a register. Add 1 to that thing. And then store. Take the register and put it back into memory where it was before. This is not something that matters to us right now in terms of file systems directly. However, when we get to thinking about concurrency, this is where this idea of I++ is not an atomic operation. There are three things involved in incrementing a number, incrementing a value that happens to be in memory. We're going to use the word atomic in terms of disks in a couple of moments, but this is really important when we get to the idea of concurrency when we're thinking about threads of execution. There was a big shakeup here because there were lots of people on the list that are not there, but Magical Rhino has stayed at the top. Congratulations to Magical Rhino. Yes. I'm also delighted, I guess, that Drop Table Students has shown up here. I'm a little disappointed that Dragonite showed up, though. I don't know. It's the wrong kind of Pokemon. I'm not talking about the one after that. So, continuing our review of stuff that you have seen over the last few years, what I would like to do now is spend a little bit of time quickly building a linked list in C. And as we're doing this, the stuff that I want to think about includes design by contract. And so this was something that you would have seen in Comp 2160 if you have taken Comp 2160. The big idea here is I want to be able to encode assumptions that I have about my own state of code in my code, so that if those assumptions are violated, my code will stop and it will give me some information about why that assumption has been violated. It will tell me where it's happened, and it will tell me that it's happened, and it gives me ideas of how to do debugging when I get to the point of debugging. I want to think about build tools. I want to think about make. I am not at all in this course expecting you to write your own make file. I'm going to give you make files. You will modify make files, but I don't actually care if you can write a make file. I'm not going to write a make file here. I'm going to show you a make file, and I'm going to run the make command to build some software, but I'm not going to write a make file because I don't care if you can write a make file. That's not important in this course to me. Automated testing. Let's write some code to run our code and verify that the output is what we're expecting it to be, that the side effect that we've tried to build into this thing does what it says it's supposed to do. And finally, I want to do a little bit of debugging. Again, this is on the command line with LLDB, so I want to do this on our command line. If you want to use VS Code or CLion or some other IDE for developing C code, I'm more than happy for you to do that, but I can't support you for debugging. I can give you some support with LLDB, but I can't support other things just because I don't really use those other things to be able to do that. I invite you to code along with me if you have your development environment set up, if you are able to connect to Aviary already. The code that we're working with is in that C review repository. I've linked to that in the course notes for today's lecture. So the way that I got that yesterday, just to remind you, was I did git clone https://code.cs.umanitoba.ca/comp3430 summer 2025, C review. I did this, and then I had a local copy of the stuff that we're working with. So I'm going to give you just 2 seconds to catch up, to get your environment set up if you want to follow along with me. Otherwise, I'm going to keep on moving along with this stuff. I'm going to make this a little bit bigger. I'm just going to make sure, is that okay for everybody to see at the back? Yes, awesome, okay. Okay, so I'm going to change back into C review here. And the code that we're working with right now is in this directory that's called list in C review. I've got 3 files in here. I've got list.h, list.c, and main.c. I'm going to start by popping another terminal open on the side here. And I'm going to open up list.h. This is the interface that I want to implement for this list type. There are a few things that I'm doing here that I believe makes this a well-designed interface. And there's stuff that I'm doing here that you're going to see in other code that you're going to be using throughout the course. So I want to step through a little bit of this. The very first thing I've got here on line 1 is a header guard. You might have used ifdef or ifndef to be able to do this stuff. I'm just going to use pragma once because I think it's a lot nicer. It's a lot nicer than doing all that ifdef and making sure you got your endif at the very bottom of your file. I'm using pragma once to do that. On line 5 here, I'm declaring a type without specifying how that type is actually implemented. So this typedef line here says that there is a type that's called intlist, but the person or the code that's going to call these functions shouldn't and doesn't know about what that structure actually looks like internally. The only way that you should be able to work with this structure is by passing instances of it to the functions that I have implemented myself. So while I don't have a structured definition here, I've got the declaration, and that's enough for me to be able to use pointers to that type. Then I've got my constructor function. This returns a pointer to an instance of intlist. And as I said yesterday with my main function, when I explicitly don't want to have any arguments, I'm going to put void in here. This means that you cannot pass things. The compiler will refuse to compile your code if you try to pass something to this function. If you just put parenthesis, your compiler will not necessarily refuse to compile your code. It will just ignore that you're passing stuff to it. Void explicitly says you cannot pass anything to this. This is my constructor function, so I'm going to create an instance of this list, and I'm going to work with it. And I'm going to be returning this, and the list that I return to you that's empty is going to be a valid list. I'm going to have some design by contract stuff in this. This is my destructor function, so I am taking as input an instance of my list, and I'm going to return a pointer to this int list type, but the values here are going to be, I'm going to return null if I've succeeded in destroying the list. This is a convenience way for me to say things like my list is equal to destroy list, and then I can check and confirm that it has been set to null when I do that. Yes? We don't have classes because we're in C. We have a type. We've declared a type, we have a structure, but we don't have classes. The only other two operations that we're going to have on this list that we're implementing is inserting to the front of the list, because that's the easiest thing we could possibly do. So I'm going to do that, and returning the size of the list. Returning the size of the list here is something that I could say, I'm going to count the number of nodes here, or alternatively, I can just keep a property in my structure that says this is the size of the list currently. But because I haven't specified what the type's structure actually looks like, that's up to me to decide. So I'm going to open up list.c here. And in list.c, I've now got the actual structure definition. So that's the struct int list here. And I've got an int node declaration here. I don't want people using this interface to know what my node structure looks like, so I don't put it in my interface. The only thing that's in my interface is saying there's a list and you can do stuff with it, but I'm not telling you how it's actually implemented internally. So the very first thing that I want to do here is I'm going to want to start making my create list function, and I'm also going to want to start making an invariant for this data type. I want to follow this idea of good design by contract. So I want to know what it means for a list to be in a valid state. So the first thing I'm going to start with is the list constructor function itself. So int list pointer create list. I'm taking no arguments to this. In this code, there are no preconditions. I don't really have something to check if I'm not being passed anything. There's nothing that I have for state right now for me to be able to check in the first place. So I don't have any preconditions for this specific function. I don't have any preconditions, and so at that point, I can start trying to populate this list. So I'm going to declare a new variable, int list. the list. And I'm going to say that this is equal to, I'm going to use a different function this time. In 2160, generally you're using malloc to do this. calloc does approximately the same thing as malloc. calloc will take the number of members that we want to allocate and the size of each of those members. This internally does that multiplication for us that we do when we're doing malloc. When we say size of something times 10, this calloc does that internally, and it just kind of specifies a little more clearly what I'm trying to accomplish with this. So I'm going to say that I want a calloc size of int list, and I want to allocate enough memory for one of these things. So the first argument that you're right. You're absolutely right. I want to do one size of that. Thank you. This is pair programming, but with 100 peers. That's very nice. Thank you. So I want to allocate one of these things for my list. Then what I'm going to do is I want to then start populating properties of this after I've checked to see if I've actually got something back. Want to check to make sure that I've actually been able to allocate some memory. So I'm going to test to see that the value returned to me from calloc or malloc was not null when it was returned to me. If the list does not equal null, then what I want to be able to do is set properties on this list. So the list arrow dereferencing this count is equal to 0, and the list head is equal to null. I explicitly want to do this because I want to make sure that the list that I am constructing and returning to the caller is actually a valid list. And then the very last thing I'm going to do here is return the list. I want to have a post condition. I want my post condition to be that the list that I've constructed is valid. I'm going to put my post condition inside this conditional statement because if I'm returning null, things have gone terribly wrong and I don't really want to send that to my post condition because it's going to fail. It's going to fail. So I want to use my invariant that I'm building here as my post condition to check that a non-null list is a valid thing. So I'm going to start by declaring a new function. I'm going to declare this as static. Static, remember, in C means file private. It's only available for use inside this file. Other code that's using this list cannot call this function because it's been marked as static. My invariant here is going to return void. So I don't need it to return anything. It's just going to be full of assertions, and the assertions will fail if one of them has been violated. Some people choose to do this with conditional statements and then Booleans and then returning true or false, whether it's valid or not. But my strong preference is that it be void and just have assertions inside here and let them fail when it's time to fail. So I'm going to say static void validate list. And I'm going to say const int list pointer the list. My invariant should not change my list. Const here is kind of marking this as I don't want to change anything in my list while I'm validating it. So I want to make sure that as it's getting compiled that it's going to prohibit me from making changes to the thing that I'm doing. The very first assertion that I'm going to make is that the list is not equal to null. I'm going to have assert list not equal to null in every function. So I'd rather just put this in my invariant as opposed to putting it in every function and then calling the invariant separately. This is my personal design choice. You can do it however you want. Once I've asserted that the list is not null, then I can start asserting things about its properties. The only valid list that we have right now is the empty list. That's the only one that we've got. So I'm going to say that, assert that the list arrow count is equal to null, 0, and the list arrow head is equal to null. That's a valid list for me. We have count node 0, and the head of the list doesn't point to anything right now. It doesn't point anywhere in memory. It specifically is null. It doesn't have any value pointed at right now. Yeah. Sorry? Do we need count? We don't need count in the list, but I'm going to have count in the list. This is going to save me having to count the nodes every time I do this. I'm spending a little bit of memory to keep loops to a minimum here. Okay, and then the last thing I want to do here is in my post condition, I'm going to call this validate list. So notice for now that all I'm using is pointers. I haven't done any stack allocated variables except for like primitive types, and I've got structures and stuff that have primitive types. But all the stuff I'm doing is dynamically allocated memory. None of the stuff is stack allocated memory yet. I'm going to zoom out of this for now. Whoops. I'm going to open list.c again, and I'm going to zoom out of this. I'm going to quit my manual page. I'm going to change directory back one here. I'm going to make this. I'm going to cross my fingers and really hope that it works. Okay, awesome, it worked. Yeah, okay. Awesome, it worked, I say confidently, but when it compiles, in reality, it may not actually work the way that I want it to work, but good enough for now. The next thing I want to start doing is I'm going to change back into list here, and I'm going to open up main.c. I want main to actually start calling functions here. I want to start making main do something with the list structure that I'm working with. So I'm going to now say in main, the very first thing I'm going to say is int list pointer my list is equal to create list. I'm going to call the function here. My main.c here is going to be my suite of automated tests. And really the only thing I can do with this right now is confirm that the thing that I got back from my constructor function is not null. So if my list does not equal null, or more likely if it is equal to null, I'm going to say fprintf. Did you use fprintf at all when you were in 2160 anyone? Some of you did? Okay. I'm going to do fprintf. You might not have seen this before. Please just accept it for now. But I'm going to say fprintf stderr. So in 2160, you did standard output and standard input. Standard error is a lot like standard output, but it's specifically for error messages and that sort of thing. So I'm going to say fprintf stderr, and I'm going to say my list is null. New line, write that out. Yeah.
That won't ever, like, we won't ever reach that, so because of the assertions that we have.
Ideally, we will not, no. However, when we're testing our code, generally we want to test it without assertions turned on at all. Yeah. So I'm going to quit this, and I'm going to make this. I'm going to make, so right now I'm in the list directory. I'm going to say make -c. That says change directory to the parent directory. So -C and then .. says go to the parent directory to find the make file. I'm going to run that. It compiles, excellent. I'm going to zoom into list here, and I'm going to run main. Nothing happened. Awesome. That means that we were able to construct this list, and we didn't get null back, which is great. That's really, really excellent. So now I want to do something a little more interesting. So I'm going to go back to list.c. I'm going to go down to the bottom, and I want to start implementing another part of my interface here. The other part of my interface is that I want to check the size of the list. The size of the list should be quite a simple function for us. I want to be able to return something that is the count of the number of items in this list. I'm going to say int list size. This is marked as const because I don't want to change my list structure as I'm passing it to this function. This should have no side effects. The precondition that I have here is that we have a valid list. So I'll call my invariant validate list, the list. And I'm going to separately check to see that the list is not equal to null. So this is to the question that you just had. We're never going to reach that state if we have these assertions turned on. When I turn the assertions off, I still don't want my code to crash. I want it to return null or something, but I don't want it to crash. Yeah?
If the list has one element, I think your validate list will always fail.
You're right. If my list has anything that's not 0 elements, it's definitely going to fail. And that's, at least for now, that's on purpose.
Okay.
We're going to make that change when we get to inserting something to the front of the list. And then we'll start counting the nodes and validating that it has the correct number of nodes for the counter. Yeah. But you're right. You're 100% right that this is going to crash every time we try to run it as soon as we start inserting things into our list. Yeah.
So, but validate list, like we were talking about, we don't want assertions to be running at all, right? But when you send this to production or whatever. So, but validate list is just assertions. So should we not assert validate list, like returning the Boolean from validate list if I'm going to just go through and just assert that as well? So validate list doesn't actually get run.
So what we're going to do ultimately is that validate list here, when we are compiling our code, we can pass an option to our compiler to turn assertions off.
Yeah.
And that effectively makes them like no op. Nothing happens in those statements. Our compiler is going to be able to say, this is a function that gets called and it's just full of no ops. Yeah. And our compiler is then going to say, don't do anything because it's just full of no ops when it's doing that. Yeah. Yeah. What does it say when it runs? Oh, good. I was actually trying to get mine to say that and it wouldn't do it. Yours is failing successfully in the way that I was trying to make mine fail, and then it just wasn't failing. So give me a second to try and get into the same state that you're in right now. So I want to go back to my count function here. I'm going to change the name of this to the list. I'm going to make this again. I'm going to return I'll say -1. I believe that's what my interface says. And I'll say count is equal to the list arrow count. Here's what I'm going to do, because I really want to see that failure. I want to demonstrate the failure that you're seeing here. So I'm going to copy this over to Aviary. I'm not prompted for a password because I've changed my configuration for Aviary.
Do that for us.
So if you want to do this on Linux, you have to use the password SSH copy ID. This is a program that you can use to copy a public key to a remote system. And then this is doing public key authentication. So you don't have to enter a password. I'm going to make clean. I'm going to make this again. I'm going to go to list and I'm going to run main. Oh no, nothing's happening. So I'm going to use my debugger to see what's going on with my code. I'm going to run LLDB on main. LLDB is my debugger. I'm trying to find, this is absurd. I'm trying to find out why this code is not crashing right now, as opposed to why this code is crashing. I'm going to run LLDB on the program that I've compiled, and I'm going to set a breakpoint at my main function. So I'm going to do B for breakpoint, and then main. You can also pass line numbers to this if you want to break on a specific line number, as opposed to breaking on the main function. And then once you set a breakpoint, you can press type an R to run. And if I go to S here to step into this function, so I want to step into the create list function, so I'm using S. It's doing calloc. It's testing to see if it's not null. It's allocated this thing. So I'm pressing N here to step to the next line. I'm baffled why this is not failing for me, but it is failing for you. It should be running the main function. Okay. Oh gosh, now I have to figure out why this is not crashing for me, because I want it to crash. I desperately want this to crash. I desperately want this to fail. Yeah. Why is it supposed to fail? That is an excellent question. So I'm going to take a look at my make file here. And one of the things that I've added here is this fsanitize address. The idea for this is that the address sanitizer is something that will help keep track of things like you've allocated memory but not freed it. And it will try to keep track of things like you've gone past the end of an array when you tried to write to something, or you've gone past the heap allocation that you've made. And it will tell you about that. And it will tell you what line of code you allocated that thing on, and it will tell you what line of code you either leaked it on or what line of code your failure was happening on. Can you come to see me after class and show me what you're getting as output? Because I really, really want to see that. Okay. So for now, I'm actually happy enough with the stuff that we have seen in terms of writing some C code here. I'm going to work through a little more of this, and I'm going to push it up to the repository on Aviary so that you can see this worked a little bit further than it is right now. But I do want to step into taking a look at our hard disk drive before we get too far to the end of class today. So I'm going to pop back over to my slides here. And what I want to do is take a tour of a physical drive for the purpose of defining some of the terms that we've got here. So I want us to be able to define terms like the interfaces to the drive. I want us to be able to define terms like the platters that we have on the drive, the surfaces that we have on the drive, cylinders, the read-write heads, and then, really specifically, the term that I want us to be able to define by the end of today's class is the word sector. That is the most important word. It's not in this list, but it's still the most important word, and we're going to see it so many times over the next few days that you're going to be sick of hearing the word sector over and over again. But that's the key word that we've got here. So I'm going to pop back over to OBS, and I'm going to switch to my big camera, and I'm going to change to my full screen projector mode again. Hello, everybody. And what I've got here is a hard drive. This is my hard drive. This is my hard drive. This is my actual hard drive. This is an older drive. This is a 250 gigabyte drive. It's pretty old. It's relatively small in terms of the capacities that we're working with in terms of drives these days. On the very bottom here, this part right there, where these gold little tips are on the drive itself, there, where these gold tips are, this is the interface for our drive. So in a machine, the way that we're going to connect this to the main board that we have in our PC is going to be through a cable, and this interface is called serial ATA. There are a bunch of different kinds of interfaces for drives. There's serial ATA, there's IDE, and then there's SAS, which is another kind of connection for drives to be able to connect over an interface. There's a lot of other stuff that's on this board, and it may surprise you to find that this is actually an entire computer that's on this board. We'll talk a little bit more about that later in the course, but this entire thing is an entire system. And we've got basically through this interface, the main board that we have in our system is communicating to this entire computer that we have here. This chip right here that's really, really blurry right now, that is the CPU for the hard drive that we have on the system. The one that's labeled Hynix beside it is a tiny little bit of RAM that this system has. This is memory that this computer has on this system. This is the cache that our hard drive would have for reading stuff across it. The interesting stuff, though, is on the inside of this drive. And it's going to be really, really hard to get it to focus on a lot of this because it's a reflective surface. But I've got my pointing device here. This is a bent up paper clip, but this is my important pointing device because my fingers are too fat for this. The things that we need to see about this are this part right here. This is a platter. This is a piece of metal that's in this disk. This drive has 3 platters, 1, 2, and 3. Each of these platters has 2 surfaces on it. There's a top surface and a bottom surface. The thing that's reading and writing data from the surfaces of this drive are these things right here. These are the read and write heads, and you can see that for the 3 platters that we have and 6 surfaces that we have, there are 6 read and write heads. 1 for the top, 1 for the bottom, 1 for the top, 1 for the bottom, 1 for the top, 1 for the bottom. These move across the drive like this. So they scan across the surface of the drive like this. And the way that this drive works is that this spins. This spins really fast. This drive spins at 7,200 RPM, but other drives can spin twice as fast as this, up to 15,000 times per minute, which is insanely fast. These are moving really, really fast, and these read and write heads are actually sitting on the surface of the drive, like buffered by the air momentum that's caused by this thing spinning around really, really quickly. On the surface of our disk here, we've got circles. We've got circles, and that's the important part. So across this disk, we are going to have a bunch of circles that are not like wibbly wobbly like this, but actual circles. And I'm going to draw a few of these across the surface of the disk. This is a Sharpie, if anybody cares. Although, to be clear, there's a bunch of fingerprints, and people have previously scratched my name on the surface of this disk, so it's not readable anymore. What we've got here is that each of these circles that we have across the disk, these, I cannot write upside down, so I'll turn this for you in a second. Each of these are called tracks. So every one of those circles on the surface of a disk is called a track. So what I've drawn here right now is that there's 3 tracks on the surface of this disk. This disk has 3 platters on it, and every track that's on top of another track in the same location, that whole structure is called a cylinder in this disk. So all the tracks on all the surfaces that are here, this is one cylinder. All the tracks that are on all the surfaces here, this is another cylinder, and all the tracks that are on all surfaces here is another cylinder on this disk. Yeah?
6 tracks per cylinder?
For this disk, there would be 6 tracks per cylinder. Other disks are going to have more or fewer platters and more or fewer surfaces than what we've got. Each of our tracks on a surface are going to be divided into sectors. And now this is geometry. This is like going back to high school geometry. This is a sector of a circle. This is I mean, that's the word that you use when you're describing part of a circle in geometry, and that's the word that we're going to use to describe this part of a disk, is that this and each of these things that we have across all parts of that disk is a sector. So this disk is going to have sectors that are going across all the tracks on its surface. And from our perspective, in terms of file systems, what we're going to start thinking about tomorrow is that we, as an operating system, are able to address sectors on the disk. This sector here, I'm going to arbitrarily say is sector 0. The next sector after that is sector 1. The next sector after that is sector 2. The next sector after that is sector 3. 4, 5, 6, ... and so on. So these concentric rings are going to have contiguous sectors. The sector number will change slightly as we move in and out across the surface of this disk. But really importantly, we've got sectors. That is the atomic unit for our drive. Drives make a promise that is, I can either fully write a sector or I will not write anything. Sectors have sizes in bytes. Typically, it's 512 bytes. We're going to see this lots more. You don't need to memorize that right now. I promise we're going to see this number again. Modern drives have 4 kilobyte sector sizes, but drives like this one would have 512 byte sectors. Yeah.
Different with the size of the sector because it's a cone?
You're right. The sectors are physically bigger on the outside, but as far as we are concerned, and this is us as an operating system, and we don't care, it's really distracting to see myself in this image here. We don't actually care about the physical makeup of this drive beyond the abstract idea of a sector. It doesn't matter how physically big it is when we're thinking about it. All right. I'm going to pop back over here. I've put this diagram here for your reference in the slides. You are welcome to look at this. This has all the same terms that I just used pointing at this physical drive if you want to take a look at this later. At this point, you are able to list and describe data structures from previous courses. I'm going to finish working up this list example, but you should be able to describe and apply concepts like design by contract, automated testing, memory management, and debugging. You are able to describe parts of a computer architecture. You're able to decide how high-level programming languages are translated to run on a computer. And at this point, you should be able to describe some of the physical characteristics of a drive using terms like sector and cylinder and track, surface and platter. That's it for today. I hope that you all have a great rest of your day, and I will see you tomorrow. Bye, everyone.